Hey everyone, welcome to this explainer. I am absolutely thrilled you're here today. We are building a masterclass tutorial to figure out exactly how invisible magnetic forces literally power our modern world. I mean, if you've ever stopped and wondered about that secret, unseen hand making practically all your electronic devices tick, well, you are in exactly the right place. We're going to decode the whole intimate relationship between electricity and magnetic fields.
Okay, so here's our roadmap for today. We're going to start with the famous compass anomaly, cover the core magnetic force rules, figure out how to calculate those fields, and then, the really fun part, see how this all actually powers your home appliances. We'll wrap up with how to measure currents, and finally, a quick exam study guide if you're prepping for a test.
But before we get bogged down in the heavy physics, let's start with a super practical question. How does a flowing electrical current actually spin the blades of the fan in your bedroom? Or, your blender or your washing machine? How are we harnessing these completely invisible forces to make physical objects move in our everyday lives? Keep that bedroom fan in your head as we go through this, because by the end, you're going to know exactly how it works.
All right, let's kick things off with step 1, the compass anomaly.
This whole thing starts with a famous, totally accidental discovery that kind of changed physics forever. Picture this, it's the year 1820. A physicist named Hans Christian Ørsted is giving a lecture, and he casually notices a compass needle just twitching wildly every time he turns on a nearby electrical wire. That one little accident set off a massive chain reaction. After 1820, André-Marie Ampère started formulating hypotheses that all magnetism is basically generated by circulating currents. And then, jumping to 1864, James Clerk Maxwell swoops in and mathematically unifies electricity and magnetism into one beautiful framework. And what we're looking at here just brilliantly illustrates exactly what Ørsted saw on his desk. When the current is off, the compass points north, perfectly happy, naturally aligned with the Earth's magnetic field from our planet's liquid iron core. But flip that current on, the needle violently swings into this tangential deflection. It proved, without a doubt, that an electric current generates its own magnetic field in circular rings right around the wire. And think about how wild that is. The Earth's magnetic field is about 3.6 times 10 to the negative 5 teslas. To put that into perspective, Ørsted's simple everyday wire generated a field strong enough to locally overpower the magnetic pull of an entire planet. Just incredible.
Moving right along to step 2, magnetic force rules.
So, now that we know moving electricity actually creates a magnetic field, how do we handle this mathematically? Well, we use the absolute golden rule of electromagnetism, the Lorentz force law. The equation is F equals Q times E plus V cross B. Basically, this calculates the exact push and pull a charged particle feels when it's moving through electric and magnetic fields. F is the resulting force vector, Q is our experiencing charge, V is the velocity, how fast and what direction it's going, and B is the magnetic field itself.
Now listen up. If you're taking notes for an exam, you absolutely need to remember these constraints. First rule, the magnetic force is 0 if the charge is perfectly stationary. If that velocity is 0, there is no magnetic force, period. Second rule, the force is also 0 if the velocity and the magnetic field are perfectly parallel to one another. And lastly, for your units, keep in mind that 1 Tesla is dimensionally equivalent to a Newton-second per Coulomb meter. Jot that down for sure. Let's see how this all builds up from a single microscopic particle to a macroscopic wire. An electron moving inside a wire is kind of like a tiny car driving on a highway. To find the total force on the whole highway, we basically follow 4 logical steps. We assume a mobile charge density, calculate the total force on all those little carriers, map that over to the current density, and finally, we arrive at our macroscopic result, F equals IL cross B. In plain English, the force on a wire equals the current times the length vector crossed with the magnetic field.
Okay, on to step 3, calculating magnetic fields.
Right, so we understand how the force pushes on our wire, but how do we mathematically define the invisible field that's doing all the pushing? For that, we use the Biot-Savart law. But honestly, it helps to compare it to something you probably already know, Coulomb's law for static electricity. It's really like comparing apples and oranges. Coulomb's law relies on a simple scalar charge, just a point emitting an electric field symmetrically in every direction. But the Biot-Savart law for magnetic fields, it's a lot trickier. It uses a vector element, the current and its direction, and the resulting field is highly dependent on the angle. In fact, it produces literally 0 field straight along the axis of the current itself.
Which brings us to step 4, powering home appliances, my favorite part.
We've done the history, we've looked at the formulas, but how does this complex math actually power your blender? Well, when you put a loop of wire carrying a current inside a magnetic field, the opposite sides of the loop feel forces pushing in opposite directions. One side gets pushed up, the other side gets pushed down. This creates torque, and torque is essentially just a twist. This exact twisting motion, calculated as the magnetic moment crossed with the B field, is the hidden hand that spins literally every electric motor in your house.
And motors aren't the whole story here. If we take that wire and tightly coil it into a helical shape, called a solenoid, something really amazing happens. It acts like a magnetic trap. By capturing and concentrating the field inside its core, we can create incredibly strong, uniform magnetic environments. This exact solenoid architecture is the foundation for relays, industrial electromagnets, and yes, even those massive, life-saving MRI machines at your local hospital.
Next up, Step 5, measuring electrical currents. For engineers, safely harnessing all this incredible power means we have to measure it accurately, right? And we have to do it without breaking or changing the circuit we're testing. So we use a moving coil galvanometer, which actually relies on that exact same twisting torque we just talked about to physically move a needle on a dial. But notice how adapting this basic device requires solving some really clever engineering problems. If we want to measure current, we build an ammeter. But to avoid choking off the current, we have to place a tiny shunt resistance directly in parallel. On the flip side, to build a voltmeter, it needs to be placed in parallel to the circuit, which demands a massive resistance placed in series with the galvanometer. Otherwise, it would steal the very current it's trying to measure.
And that brings us to Step 6, the exam study guide.
We have covered an immense amount of ground today, so let's synthesize all of this into the ultimate cheat sheet for your exam prep. Grab your pen, here's your summary. First, the official definition of 1 ampere. It's the steady current that produces exactly 2 × 10 to the -7 newtons of attractive force per meter between 2 infinitely long parallel wires. Second, and this is a classic trick question, so watch out, if a particle enters a magnetic field perfectly perpendicularly, it moves in a circle, and its cyclotron frequency is completely independent of its velocity. I repeat, independent of velocity. Third, both Biot-Savart and Coulomb's laws obey the principle of superposition. And finally, if a particle enters a magnetic field at an angle, the parallel velocity drags that circular motion out into a stretched-out helical spiral.
So here is our master blueprint. Charges in motion create magnetic fields governed by Biot-Savart and Ampere's law. And conversely, those magnetic fields exert force right back onto moving charges governed by the Lorentz force. These two pillars branch down to create the motors, the solenoids, and the galvanometers that pretty much run our entire modern lives.
As you look around your home today, at the fans spinning, the appliances humming, I really want to leave you with a final provocative thought. Looking at this perfect, beautiful reciprocity of nature, ask yourself, are electricity and magnetism truly 2 separate forces at all? Or are they actually just reciprocal manifestations of the exact same fundamental phenomenon? Keep questioning, keep learning, and thank you so much for joining me on this explainer.